What does eternity look like? Close your eyes for a moment and try to picture it. An endless expanse of time stretching forward with no horizon, no final chapter. It's an idea so vast it makes the mind reel, and yet this is the fate that awaits our universe, not in some distant, abstract sense, but as the inevitable conclusion to a story that began with the Big Bang. Right now, as you watch this, the cosmos is unfolding towards an ending so profound it reshapes everything we think we know about existence itself. The stars above you, the planets, even the atoms in your body, they're all part of a cosmic countdown to a finale that defies imagination. But here's the thing, the universe doesn't just fade to black like the closing scene of a movie. Its ending is stranger, more intricate, and far more awe-inspiring than anything we could script. Scientists and philosophers have spent centuries wrestling with this very question, peeling back layers of reality to uncover clues about how it all concludes. Some theories suggest a slow, cold unraveling over trillions of years, where galaxies drift apart like lonely ships in an ever-expanding sea. Others hint at a fiery collapse, a dramatic reversal of everything we know. And then there are the possibilities that blur the line between science and philosophy, ideas so radical they challenge our very understanding of time, space, and meaning. This isn't just a story about the distant future, it's a mirror held up to humanity's deepest questions. Why are we here? What does it mean to exist in a universe with an expiration date? And if the cosmos is truly headed for an end, does that change how we live today? Over the course of this journey, we'll explore the most compelling theories about the universe's ultimate fate, from the chilling embrace of heat death to the speculative rebirth of cyclic cosmology. We'll dive into cutting-edge research, hear from the scientists racing to unravel these mysteries, and confront the profound implications of a cosmos that doesn't last forever. So take a deep breath, because by the time we're done, you'll never look at the night sky the same way again. Picture the universe not with a bang, but with a whisper, an endless, silent exhale stretching across time so vast it dwarfs all of human history. This is heat death, the most widely accepted theory for how our cosmos might meet its end. It all comes down to entropy, that relentless force driving everything from melting ice cubes to dying stars toward a state of perfect, unchanging equilibrium. Think of it like a cup of coffee left on the counter. No matter how hot it starts, eventually it cools to room temperature, its energy dissipated into the air. Now scale that up to cosmic proportions. Over trillions upon trillions of years, every star will exhaust its fuel, every black hole will evaporate into faint radiation, until the universe becomes a thin, lukewarm soup of particles so spread out that no new structure can ever form again. But here's what makes this scenario so haunting. It's not just about cold and darkness. It's about the irreversible loss of possibility. Right now, the universe crackles with activity. Galaxies collide, novas explode, planets stir with chemistry that could spark life. In a heat-death reality, none of that remains. Space itself keeps expanding, pushing matter so far apart that atoms might as well be alone in the void. Even time loses its meaning, because without change, without stars to orbit or energy to transform, there's nothing left to measure. It's like a clock ticking in an empty room forever. Some researchers frame this as the universe's ultimate act of forgetting. All the information encoded in the arrangement of particles, from Shakespeare's sonnets to the rings of Saturn, gradually smears into uniformity. No memory, no structure, just a featureless expanse where nothing happens forever. And yet, there's a strange beauty in this inevitability. The same laws that gave us swirling nebulae and beating hearts are the ones that guarantee this quiet finale. It's a reminder that existence isn't just about permanence, it's about the fleeting, luminous moments against the dark. Now imagine a different kind of end, one where the universe doesn't fade quietly into cold emptiness, but instead is torn apart piece by piece in a violent cosmic crescendo. This is the Big Rip, a scenario so extreme it makes heat death seem almost gentle. It all hinges on dark energy, that mysterious force causing the universe's expansion to accelerate. Right now, its grip is subtle, just strong enough to push galaxies apart. But what if it keeps getting stronger? Picture a rubber band stretched tighter and tighter until it finally snaps. That's the fate awaiting our cosmos if dark energy's influence grows unchecked over time. The first signs would be almost poetic in their devastation. Billions of years from now, the space between galaxies would stretch so rapidly that entire clusters, once bound by gravity, would be wrenched apart. Neighboring galaxies would vanish over the cosmic horizon, their light stretched beyond detection. Then it would come for the stars, our own Milky Way, ripped into strands of glittering debris. Solar systems would unravel next, planets torn from their orbits as the fabric of space itself pulls harder than the sun's gravity can hold. But the most chilling moment, when the rip reaches down to the scale of atoms, even the forces holding molecules together would lose their grip, reducing everything, your phone, the Eiffel Tower, even your own body, into a chaotic spray of subatomic particles. Here's where things get even stranger. Astronomers have noticed something odd in recent measurements of the universe's expansion rate, a discrepancy called the Hubble tension. Different methods of calculating how fast space is stretching don't quite agree, and one possible explanation is that dark energy isn't constant. It might be evolving, growing more potent over time. If that's true, the Big Rip isn't just speculative fiction, it's a mathematical inevitability waiting in the distant future. What makes this theory so unsettling isn't just the scale of destruction, but the timeline. Unlike heat death, which plays out over almost unimaginable eons, the Big Rip could happen relatively quickly once it begins. In the final minutes, space would expand faster than the speed of light, shredding atomic nuclei into quarks before even those fragments are ripped apart. The universe wouldn't just end, it would dissolve. Yet amid this cosmic violence, there's a tantalizing question. Could we detect the early warning signs? Some physicists suggest that if dark energy is strengthening, we might find clues in the way distant supernovae brighten and fade, or in subtle wrinkles in the cosmic microwave background. It's a race against time, not just for humanity, but for any civilization hoping to glimpse the universe's fate before the curtain falls. Because if the Big Rip is real, there won't be a second act. Just an empty stage where the universe once was. The Big Rip paints a picture of cosmic disintegration, but there's another possibility, one where the universe doesn't tear itself apart, but instead turns inward in a dramatic reversal. Imagine the expansion of space, which has been carrying galaxies apart for billions of years, suddenly slowing, then stopping, then reversing. Gravity, the silent architect of the cosmos, would finally overcome dark energy's push, pulling everything back together in a collapse so complete it mirrors the Big Bang in reverse. This is the Big Crunch, a scenario where the universe folds back into a singularity, a single point of infinite density, as if hitting the rewind button on creation itself. What would that look like? At first, the changes would be subtle. Distant galaxies, now rushing away from us, would gradually slow their retreat. Over billions of years, they'd stall, then begin streaming back toward us, pulled by gravity's unrelenting grip. The cosmic microwave background, the faint afterglow of the Big Bang, would grow warmer as space contracts, heating up until it outshines stars. Then comes the violent finale. Galaxies merging in chaotic collisions, stars crammed so close together they ignite chain reactions of supernova, and finally, all matter crushed into a seething, ultra-hot plasma. The universe, once vast and cool, would end as a fiery speck smaller than an atom. But here's where it gets even more mind-bending. Some theorists suggest the Big Crunch might not be an ending at all, just a pivot in an endless cycle. If the singularity at the crunch's core rebounds, it could trigger another Big Bang, birthing a fresh universe from the ashes of the old. This is the cyclical model, a cosmic phoenix rising again and again. Each cycle would have its own unique physics, its own arrangement of matter, perhaps even its own laws of nature. Our universe might just be one page in an infinite cosmic book, endlessly rewritten. There's a haunting elegance to this idea. It answers one of cosmology's biggest questions: what came before the Big Bang? If the cycles are eternal, there's no before, just an infinite loop of expansion and contraction. Yet evidence for this theory remains elusive. The critical factor is the balance between dark energy and gravity. Right now, dark energy dominates, pushing galaxies apart. But if it weakens over time, or if gravity somehow gains the upper hand, the scales could tip toward collapse. Some versions of string theory even suggest extra dimensions could influence this balance, making the crunch inevitable. Of course, the cyclical universe raises profound philosophical questions. If the cosmos resets endlessly, are we doomed to repeat the same story, or does each cycle bring something new? Could information or even consciousness somehow persist between universes? And if the Big Bang wasn't a beginning but a rebirth, does that change how we define time itself? These aren't just thought experiments, they're windows into the deepest mysteries of existence, where science brushes against the metaphysical. For now, the Big Crunch remains a tantalizing what if. Observations show the universe's expansion is accelerating, not slowing, making collapse seem unlikely. But science has surprised us before. Perhaps dark energy will fade, or gravity will reveal hidden strength. Or perhaps the cycles operate on timescales so vast we'll never witness the turn. Either way, the idea of a universe that breathes, expanding and contracting like lungs, offers a poetic counterpoint to the bleakness of heat death or the chaos of the Big Rip. It's a reminder that endings can also be beginnings, and that the cosmos might have rhythms we're only beginning to sense. There's a theory about the end of the universe so bizarre it sounds like science fiction, yet it's rooted in the very laws of quantum physics. Imagine a single microscopic bubble forming somewhere in the depths of space, so small it's invisible to the naked eye. But this bubble isn't made of air or water. It's a pocket of true vacuum, a state where the fundamental laws of physics are rewritten, and it's expanding at the speed of light. This is vacuum decay, a catastrophe that wouldn't just destroy the universe as we know it, it would erase the very rules that make existence possible. To understand why this is so terrifying, you need to picture the universe as a landscape of energy fields. Right now, we exist in what physicists call a false vacuum, a stable but precarious state, like a marble resting in a shallow dip on a hillside. It's comfortable here, but there's a deeper valley below, a state of lower energy the universe could drop into if given the right nudge. If that happens, the marble starts rolling downhill, and the laws of physics as we know them cease to exist. The bubble of true vacuum would expand outward, rewriting reality at its edges. Atoms would disintegrate, forces like electromagnetism and gravity would unravel, and every structure in the universe, from planets to people, would vanish in an instant. What's truly chilling is the speed. Once the bubble forms, there's no warning, no time to react. It moves at light speed, meaning the first sign of destruction would be the destruction itself. One moment you're sipping coffee on Earth, the next the bubble reaches our solar system, and everything, the coffee, the cup, your hand, dissolves into particles governed by entirely new laws. And because it expands at the speed of light, you wouldn't even see it coming. But here's the twist: this isn't just doom-mongering, the math checks out. Quantum fluctuations happen all the time, tiny, random shifts in energy at the subatomic level. Most are harmless, but if one triggers a phase transition into the true vacuum, the domino effect is unstoppable. Some researchers argue that if vacuum decay were possible, it likely would have happened already, given the universe's age. Others counter that we might just be in a particularly stable pocket of space-time, a cosmic roll of the dice that hasn't come up zero yet. The strangest part, if true vacuum exists, it might not be bad. The new physics inside the bubble could allow for unimaginable forms of energy or matter, just nothing recognizable to us. Life, stars, even the concept of time might take on entirely different meanings, but for us, in this universe, it would be the ultimate reset button. A silent, swift end to everything, not with fire or ice, but with a quantum whisper. So why haven't we seen signs of vacuum decay? Maybe it's extraordinarily rare. Maybe the universe is more stable than we think, or maybe, just maybe, the bubble is already on its way, and we're living in the last peaceful moments before the cosmic rules change forever. That's the unnerving beauty of quantum physics. Even in stillness, the universe hums with potential annihilation. All it takes is one tiny bubble to rewrite the story of everything. The last star in the universe isn't snuffed out in some dramatic explosion. It fades like a dying ember, its light growing dimmer and redder until it vanishes into the endless dark. This is the beginning of the black hole era, a time so incomprehensibly long it makes the age of stars look like the blink of an eye. With no new stars being born, the cosmos becomes a graveyard of relics. Rogue planets adrift in the void, their surfaces frozen to near absolute zero, and black holes, the final rulers of this twilight epoch. At first, these black holes might seem like the last bastions of structure. They'll continue to consume any stray matter that drifts too close, their event horizons flickering with faint radiation as they slowly bleed energy into the void. But even they aren't eternal, thanks to Hawking radiation, a quantum quirk predicted by Stephen Hawking. Black holes aren't truly black, they leak particles, shedding mass over time. The smaller the black hole, the faster it evaporates. Stellar mass black holes might take 10 to the power of 67 years to vanish, while supermassive ones could linger for 10 to the power of 100 years. That's a 1 followed by 100 zeros, a time span so vast it defies human intuition. Now picture the universe in this era, an expanse so stretched by expansion that even black holes are isolated islands, each separated by distances beyond imagination. No galaxies, no stars, just the occasional whisper of Hawking radiation as these cosmic titans slowly dissolve. The temperature of space itself hovers just above absolute zero, colder than anything we can conceive. And yet, even here, there's an eerie kind of activity. When a black hole finally winks out of existence, it releases one last burst of energy, a final spark in an otherwise silent cosmos. But what happens when even the black holes are gone? The universe enters its darkest chapter yet, the age of dark matter and radiation. Without stars or black holes, the only structures left are the faintest gravitational imprints of long-dead galaxies, their dark matter halos still drifting through the void. Even these will dissipate over time, their particles stretched so far apart that gravity can no longer pull them together. Space becomes a near-perfect vacuum, its energy density diluted to almost nothing. This is the ultimate in point of entropy, a universe where nothing happens because nothing can happen. No more chemical reactions, no more motion, just an endless sea of particles so sparse they might as well be alone. Time loses all meaning because without change there's no way to measure it. It's a cosmos that's forgotten how to be anything but empty. Yet even in this desolate future there's a strange kind of poetry. Every black hole's evaporation, every particle's slow drift into isolation, is the universe playing out the final consequences of the laws that once birthed galaxies and life. The same physics that gave us supernovas and solar systems also guarantees this quiet, inevitable fade. It's a reminder that existence isn't just about beginnings, it's about endings too, and the breathtaking scale on which they unfold. Even the protons that form the building blocks of everything you see, your body, the chair you're sitting on, the stars in the sky, aren't truly eternal. In a universe stretched across unfathomable eons, they too will meet their end. This is proton decay, a process so slow it makes the lifespan of black holes seem fleeting. Current theories suggest that after 10 to the power of 34 years, that's a 1 followed by 34 zeros, protons themselves might disintegrate, unraveling the last traces of matter into nothing but radiation and subatomic wisps adrift in an endless void. Here's how it would unfold. Right now, protons are staggeringly stable. The average proton in your body has likely existed since the first moments after the Big Bang, nearly 14 billion years ago. But in the extreme timescales of the far future, even this stability has a limit. Quantum mechanics hints that protons aren't indestructible. They could very rarely break apart into lighter particles, perhaps a positron and a neutral pion before those two decay into pure energy. Picture a sandcastle on the beach, grain by grain, vanishing in the wind. Now imagine that sandcastle is every atom in the cosmos, and the wind blows for longer than the universe has currently existed. That's proton decay. The implications are staggering. Without protons, atoms cease to exist. No more hydrogen, no oxygen, no carbon. The elements that make up planets, stars, and life itself dissolve into a sea of radiation. Even the remnants of dead stars, the cold iron cores of white dwarfs or the neutronium hearts of pulsars, would gradually crumble into this formless haze. The universe, once rich with structure, becomes a featureless bath of photons and leptons, so thin and spread out that particles might never interact again. But here's the twist: we don't know for sure if proton decay is real. Despite decades of sensitive experiments like detectors buried deep underground, shielded from cosmic rays, no one has ever observed a proton decaying. Some versions of grand unified theories in physics predict it should happen, while others suggest protons might be truly stable. If they do decay, it's so rare that observing it would be like watching a single grain of sand in a desert, waiting for it to spontaneously combust. Yet if protons do vanish, it reshapes the timeline of the universe's in-game. Earlier, we talked about black holes evaporating over unimaginable spans of time. But if protons decay first, they'll erase matter long before black holes finish their slow fade. The cosmos would transition from a realm of black holes and drifting particles to a near nothingness, where even the memory of solid objects fades away. There's a haunting beauty in this idea. All the complexity of the universe, the swirling galaxies, the DNA in your cells, the sound of laughter reduced to its simplest, most elemental form. No drama, no catastrophe, just the quiet unraveling of the threads that hold reality together. It's a reminder that eternity doesn't favor anything, not mountains, not stars, not even the particles that make them. In the end, all that's left is light drifting through an infinite dark. Even in the deepest emptiness of space, what we might call true nothingness, there's a hidden flicker of activity. Quantum mechanics tells us that a perfect vacuum isn't truly empty. Instead, it crackles with fluctuations, tiny bursts of energy where particles and antiparticles spontaneously appear, collide, and vanish in fractions of a second. On human timescales, these flashes are inconsequential, but stretch time across eternity, and these same quantum ripples could become the seeds of an entirely new cosmos. This idea, known as vacuum genesis or quantum tunneling, suggests that an infinitely old universe might not just fade into darkness, it could give birth to fresh beginnings. Picture a bubble forming in a boiling pot of water, but instead of steam, it's an entire universe budding off from the old one. These baby universes would inflate rapidly, their own physics and constants possibly different from ours, branching into realities we can scarcely imagine. It's like cosmic reincarnation, a phoenix rising not from ashes, but from the quantum foam of spacetime itself. The mechanics are mind-bending. In the far future, when our universe has expanded into near nothingness, quantum fluctuations don't stop. Given enough time, say 10 to the power of 10 to the power of 56 years, a random fluctuation could tunnel through the energy barrier separating our vacuum state from a lower energy one. This wouldn't just tweak the rules, it could spawn an entirely new Big Bang. The process is ludicrously rare, but in an eternity, even the rarest events become inevitable. What's fascinating is the scale of possibility. Some physicists theorize these new universes might inherit certain traits from their parent, like fundamental constants or dimensional structures. Others suggest they could be utterly alien, with different forces, particles, or even extra dimensions. It's a cosmic lottery where the winning ticket might birth a universe where gravity is stronger, stars burn brighter, or life takes forms beyond our comprehension. But here's the twist: we might never know. These budding universes would inflate away into their own space-time, forever disconnected from ours. They're not just distant, they're unreachable, like shadows cast on the wall of a cave we can never leave. And yet, if this theory holds, our own universe could be the offspring of another's quantum fluctuation, a bubble in an infinite chain stretching backward and forward through eternity. This idea blurs the line between physics and philosophy. If universes can arise from nothing but time and quantum chance, does that mean creation doesn't need a creator? Or does it hint at an even deeper layer of reality, a multiverse where every possible universe exists somewhere? It's a humbling thought that even in the void, the universe might find a way to begin again, rewriting its own story in the dark. And so, against the bleak backdrop of heat death or proton decay, there's this faint, flickering hope. Not for us, not for our distant descendants, but for existence itself. The cosmos might not end, it might just reboot. Let's dive into one of the most bizarre ideas in cosmology, a thought experiment so strange it makes black holes and vacuum decay seem almost mundane. Imagine floating alone in the infinite darkness of a heat-dead universe, your consciousness flickering to life for just a moment before dissolving back into the void. No body, no past, no future, just a single, self-aware thought emerging from pure randomness. This is the Boltzmann Brain paradox, and it forces us to question not just the fate of the cosmos, but the nature of reality itself. The paradox is named after physicist Ludwig Boltzmann, who wrestled with the idea of entropy and statistical mechanics in the 19th century. His core insight was simple: in an eternal universe, even the most improbable events become inevitable given enough time. Think of shuffling a deck of cards, do it enough times, and eventually the cards will align perfectly by chance. Now apply that to the fabric of reality. Over mind-boggling timescales, quantum fluctuations in the empty void could theoretically arrange particles into a functioning brain, complete with false memories and a fully formed sense of self. This brain would exist just long enough to ask, "How did I get here?" before vanishing again into chaos. Here's where it gets unsettling. If the universe truly lasts forever, Boltzmann brains should outnumber ordinary, biologically formed minds like ours by an unimaginable margin. After all, assembling a single conscious moment from random particles is statistically far easier than constructing an entire universe with galaxies, planets, and billions of years of evolution leading up to a thinking being. So why don't we find ourselves as fleeting Boltzmann brains, experiencing a brief illusion of reality, rather than as humans rooted in a consistent universe? The question cuts to the heart of what we consider real. Some physicists argue this paradox is evidence that the universe isn't eternal, that it must have a definitive end, preventing infinite time for these random fluctuations to dominate. Others propose we're missing a fundamental law of physics that prevents Boltzmann brains from forming. Then there's the spine-tingling alternative. Maybe we are Boltzmann brains, and everything we perceive from the stars above to the device you're watching this on is just an elaborate hallucination conjured by chance. But the most compelling resolution might lie in cosmology itself. If dark energy continues accelerating the universe's expansion, space will eventually stretch so thin that even quantum fluctuations can't muster the energy to create a brief spark of consciousness. The void wins and Boltzmann brains become impossible. In that case, the fact we exist as coherent, enduring observers hints that we're part of a universe where such freak accidents are vanishingly rare, or that consciousness is somehow more than just particles aligning by chance. This isn't just speculative physics, it's a mirror held up to our deepest assumptions about existence. How do we know the past is real and not just a memory fabricated in an instant? What does it mean to be you if your entire experience could be a random blip in an indifferent cosmos? The Boltzmann brain paradox doesn't offer easy answers, but it reframes the ultimate fate of the universe in a way that's both terrifying and exhilarating. It reminds us that reality might be far stranger than we've dared to imagine, and that in an infinite cosmos, even the laws of probability can bend toward the surreal. Time isn't just a ticking clock, it's the heartbeat of the universe, a rhythm woven into the very fabric of reality. But what happens when the universe grows so old and cold that this heartbeat slows, then stops? Entropy, the force that drives time's arrow forward, might hold the answer. Right now, the cosmos thrums with energy differences, hot stars against cold space, ordered galaxies amid chaos, creating the gradients that let events unfold. But in the far future, when entropy peaks and these gradients vanish, time itself could become meaningless. Picture a frozen lake at absolute zero. No ripples disturb its surface, no currents stir beneath, just perfect, unchanging stillness. That's the universe at maximum entropy, a state where every particle is spread so thin, so evenly that no work can be done. No stars ignite, no atoms bond, not even a single electron jumps between orbits. Without energy differences to exploit, the concept of before and after collapses. It's like pressing pause on reality, except there's no one left to hit play again. This challenges our deepest intuitions about time. We're used to thinking of it as a river, always flowing in one direction. But physics suggests time's arrow isn't intrinsic, it's a consequence of entropy increasing. When there's no entropy left to increase, does time still pass? Philosophers and physicists have debated this for decades. Some argue time would become a static dimension like space, where nothing changes but coordinates remain. Others propose it might cease to exist as a measurable quantity altogether, leaving a universe that's more like a frozen sculpture than a dynamic process. There's an eerie implication here. If time requires change and change requires energy gradients, then a maximum entropy universe isn't just lifeless, it's eventless. No causes, no effects, just an eternal sameness stretching endlessly. Even quantum fluctuations, those tiny bursts of randomness, would fade as space expands, leaving nothing to disrupt the silence. The phrase 10 billion years from now would lose all meaning because without change, there's no way to mark the passage of those years. Yet hidden in this bleak vision is a profound clue about reality. The fact that we experience time as flowing, that we remember the past but not the future, might not be a fundamental feature of the cosmos, just a fleeting phase in its evolution. We're living in the universe's golden age, where entropy is low enough to create structure but high enough to drive complexity. It's a narrow window in cosmic history where time feels real, where stories can be told. So while heat death paints a chilling portrait of eternity, it also frames our present as something extraordinary. Every second you're alive, every thought you have, is possible only because the universe hasn't yet reached equilibrium. Time's arrow doesn't just point toward entropy, it's the arrow that lets existence, even briefly, mean something. And when that arrow finally rests, it won't be an ending. It'll be the universe exhaling one last, endless breath. Civilizations clinging to existence in the far future wouldn't just survive, they'd rewrite the rules of reality itself. Picture a society so advanced it treats black holes not as threats but as power plants. In the era of fading stars, these cosmic engines would become the last lighthouses of energy in a darkening universe. A single rotating black hole, harnessed through structures like the Penrose process, could provide near-limitless power by stealing energy from its spin. Entire civilizations might orbit these gravitational giants, their habitats drawing sustenance from the very forces that once spelled doom. But survival would demand more than just energy. With proton decay erasing matter and space stretching into emptiness, far future minds might abandon physical forms altogether. Imagine consciousness uploaded into quantum fields, thriving in superconducting lattices or even the fabric of spacetime itself. These beings wouldn't just endure, they'd evolve beyond biology, their thoughts unfolding at speeds inconceivable to human brains, their existence measured in eons rather than years. Some theorists suggest they could encode themselves into cosmic background radiation, turning the universe's dim glow into an everlasting archive of thought. The boldest among them might attempt cosmic alchemy, creating new universes to escape the old, through unimaginably precise manipulations of space-time, perhaps by compressing matter into singularities or triggering vacuum bubbles. They could birth pocket dimensions with custom physics. These baby universes, budding off from the dying parent cosmos, might offer fresh beginnings with reset entropy, new laws of nature, and perhaps even conditions tailored for life. It's the ultimate contingency plan, not just preserving civilization, but becoming its own Big Bang. Yet even these strategies have limits. A black hole civilization might flourish for trillions of years, but eventually, Hawking radiation will dissolve their power source. Uploaded minds could face quantum decoherence as the universe cools. Pocket universes might drift forever out of reach, their creators unable to follow. This raises a haunting question: is any survival permanent or just a delay of the inevitable? Perhaps the answer lies not in permanence but in transformation. A truly advanced civilization might embrace the universe's fading, not as an end but as a metamorphosis. They could design self-replicating probes carrying the essence of their culture, programmed to awaken when new universes form. Or they might encode their knowledge into stable particles, leaving messages for whatever comes next. In this view, the end isn't extinction, it's a passing of the torch to realities we can't yet fathom. One thing is certain: the civilizations of the far future won't resemble anything we know. They'll be shaped by constraints we can barely imagine, wielding technologies that border on magic. Their struggles and triumphs will redefine what it means to exist. And though we'll never meet them, their shadow stretches backward through time, a reminder that intelligence, if it endures, will always find a way to bend the cosmos to its will. The seeds of the universe's destruction were planted in its first incomprehensibly tiny fraction of a second during the inflationary epoch that stretched space itself faster than light. This runaway expansion didn't just create the vast cosmos we see today. It locked in the physical parameters that now govern everything from galaxy formation to dark energy's grip. Imagine blowing up a balloon with microscopic variations in its rubber thickness. Those tiny imperfections would determine whether it eventually pops, sags, or deflates slowly. Inflation worked similarly, imprinting quantum fluctuations across spacetime that grew into the cosmic web of matter and set the trajectory for how it all might end. The critical factor was inflation's energy field, the mysterious force that powered exponential expansion. As this field decayed, it dumped its energy into creating particles, radiation, and the hot plasma of the early universe. But here's the twist: the exact way this field collapsed determined whether our cosmos would be born balanced on a knife's edge. Too much residual energy, and gravity would have collapsed everything back into a big crunch. Too little, and matter would have flown apart too quickly for galaxies to ever form. We exist in that improbable sweet spot where structure could emerge, but dark energy still lurks as a remnant of that primordial process. Different inflation scenarios paint radically different endings. In some theoretical models called eternal inflation, pockets of space continue expanding exponentially forever, spawning infinite baby universes with random physical constants. Our observable cosmos might just be one bubble in this multiverse foam, destined for heat death while other regions experience their own beginnings and ends. Other models suggest inflation could have ended more abruptly, creating a denser universe where dark energy never gains dominance, leading to that dramatic big crunch instead of endless expansion. The gravitational waves rippling through space from these first moments might still carry clues about which path we're on. What makes this so fascinating is the sheer fragility of our cosmic trajectory. The inflation field's decay rate had to be exquisitely tuned within about 1 part in 100,000 to produce a universe that both supports life and still allows for an eventual end. Tweaking that parameter slightly might have created a short-lived cosmos that collapsed before stars ignited, or an empty void where matter was spread too thin to ever coalesce. This fine-tuning problem haunts physicists. Is our universe's lifespan just a roll of quantum dice, or does some deeper principle select for longevity? The echoes of inflation aren't just theoretical. When we map the cosmic microwave background, the afterglow of the Big Bang, we're seeing fossilized imprints of those quantum fluctuations stretched across the sky. The pattern of hot and cold spots reveals inflation's handwriting, showing how dense regions became galaxy clusters while empty voids grew into the titanic cosmic structures we see today. Remarkably, these same fluctuations may hold hints about dark energy's future behavior. If certain gravitational wave signatures are ever detected, they could tell us whether our universe's expansion will continue smoothly or accelerate toward a more violent Big Rip. Of all inflation's legacies, the most profound might be its invisible one, the cosmological constant, a term Einstein once called his greatest blunder. We now recognize it as dark energy, the vacuum energy that's speeding up cosmic expansion. Many theorists believe this constant is literally frozen inflation energy, a relic of that primordial field's decay. If true, then the force that birthed the universe will also be its executioner, stretching space-time until stars, atoms, and time itself lose meaning. The beginning and the end, it turns out, were always connected by the same cosmic thread. Dark energy isn't just some abstract entry in a physicist's equation. It's the invisible hand shaping the destiny of everything. Right now, it makes up roughly 68% of the universe's total energy content, and that fraction is growing. But here's the catch: we have no idea what it actually is. Is it a property of space itself, as Einstein's cosmological constant suggests? Or is it something far stranger, a dynamic field that could evolve over time? The answer doesn't just satisfy curiosity, it holds the key to whether our universe ends in ice, fire, or something beyond our current imagination. Let's start with the cosmological constant, the simplest explanation for dark energy. Picture empty space not as true nothingness, but as a seething quantum foam where particle-antiparticle pairs constantly flicker in and out of existence. These fleeting fluctuations generate a tiny amount of energy in every cubic centimeter of vacuum energy that, according to Einstein's equations, should cause space to repel itself. The problem, when physicists calculate how strong this vacuum energy should be, their predictions overshoot observations by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros, the worst mismatch in the history of science. Either we're missing something fundamental about quantum field theory, or dark energy is something entirely unrelated to vacuum fluctuations. This discrepancy is known as the cosmological constant problem, and it's haunted physicists for decades. Some propose radical solutions, like extra dimensions leaking gravity away or undiscovered symmetries canceling out vacuum energy. Others suggest dark energy isn't constant at all, that it's a scalar field slowly decaying, much like the inflation field did after the Big Bang. If true, this could mean dark energy's repulsive force might weaken over time, allowing gravity to regain dominance. Or worse, it could strengthen, accelerating expansion until it shreds the cosmos in a big rip. Recent observations add fuel to the mystery. When astronomers measure the universe's expansion rate using distant supernova, they find it doesn't quite match predictions based on the cosmic microwave background. This tension, dubbed the Hubble tension, hints that dark energy's influence might be changing. Projects like the Dark Energy Survey and the upcoming Euclid telescope are mapping billions of galaxies to track expansion over cosmic time, searching for deviations from Einstein's model. Even tiny shifts could rewrite our understanding of the universe's fate. Then there's the phantom energy scenario, a nightmare version of dark energy where its density increases as space expands. In this model, repulsion snowballs uncontrollably, not just stretching galaxies apart, but eventually overcoming nuclear forces to tear atoms apart. The universe's final moments would be a crescendo of violence, space-time itself ripping at every scale. While evidence for phantom energy is scant, its mere possibility forces us to confront how little we truly know about the force dominating our cosmos. What makes dark energy so unnerving is its invisibility. Unlike black holes or neutron stars, it leaves no direct signature. We infer its existence solely through its gravitational effects. Future experiments might change that. Proposals like quantum squeezing in gravitational wave detectors or lab-based tests for chameleon particles, hypothetical dark energy carriers that hide in dense environments, could bring this shadow force into the light. Until then, we're left with a profound irony. The dominant component of the universe remains its greatest enigma, silently steering us toward a future we can predict only in broad, uncertain strokes. One thing is clear: dark energy isn't done surprising us. Whether it's a cosmological constant, an evolving field, or something beyond current physics, its true nature will dictate the universe's ultimate story. And that story, it turns out, is still being written. The universe we call home might not be the only one facing an inevitable end. It could be one among countless others, each with its own expiration date written into the laws of physics governing it. This is the multiverse hypothesis, a radical idea suggesting that our cosmos is just a single bubble in an infinite foam of universes, each with different fundamental constants, particles, and even dimensions. Picture a cosmic library where every book tells a different story of creation and destruction, some universes collapsing in fiery crunches, others fading into eternal cold, and a rare few where conditions are so finely tuned that life persists for eons longer than ours ever could. What makes this idea so compelling is how neatly it solves one of cosmology's biggest puzzles, the fine-tuning problem. Our universe's constants, the strength of gravity, the mass of electrons, the energy of empty space, are balanced so precisely that even slight changes would render life impossible. It's like dialing 1,000 knobs to exact positions just to allow stars and planets to form. In a multiverse, this isn't a miracle, it's a statistical inevitability. With infinite universes born from random fluctuations or colliding membranes in higher dimensions, a few are bound to have the right settings for complexity. The catch: most would be sterile, their physics too chaotic or too stagnant to sustain anything resembling our reality. Now consider the implications for cosmic endings. In a multiverse, heat death isn't universal, it's just one fate among many. A universe with stronger dark energy might tear itself apart in a big rip before the first stars even form. Another with weaker gravity could be so diffused that matter never clumps into galaxies at all. And in rare cases, universes might bounce endlessly between expansion and contraction, their timelines cyclical and infinite. The truly mind-bending possibility: some regions of the multiverse could harbor civilizations that have hacked their local physics, bending entropy's arrow to avoid annihilation altogether. The mechanisms that spawn these universes vary wildly. Inflationary theory suggests that during the Big Bang, pockets of spacetime could have stopped inflating at different rates, creating isolated bubbles with unique properties. String theory takes it further, proposing a landscape of possible universes arising from the way extra-dimensional strings vibrate. Some versions of quantum mechanics even argue that every possible outcome of an event spawns a new branch of reality, meaning there's a universe where heat death never comes and another where it happened yesterday. But how could we ever test such an outlandish idea? Surprisingly, there are clues. If our universe ever collided with another, the crash might have left scars in the cosmic microwave background, subtle temperature variations that telescopes could one day detect. Alternatively, the distribution of dark energy or the way black holes evaporate might betray fingerprints of higher dimensional physics. Some physicists even speculate that advanced civilizations could send messages through the quantum foam between universes, like tapping on the walls of a prison cell to reach neighbors in adjacent realities. The most humbling thought isn't just that other universes exist, it's that their endings might render ours trivial. A civilization in a cyclically rebounding cosmos could view entropy as a temporary nuisance, while beings in a universe where time loops back on itself might experience existence as an endless, repeating dream. Our heat death could be their curiosity, a cautionary tale of how not to structure a reality. And if the multiverse is truly infinite, there's a version of this script being narrated right now in a universe where the ending hasn't been written yet because for them, time itself works differently. This isn't just speculative storytelling, it's a challenge to our anthropocentric view of existence. If the multiverse is real, our universe's fate isn't special or inevitable, it's just one roll of the dice in a game without end. And that shift in perspective changes everything. Suddenly, the question isn't how will our universe end, but which kind of ending did we luck into? The answer, it seems, depends on how big reality really is, and whether our cosmos is a solo act or one line in an infinite cosmic script. The last photon in the universe doesn't blink out like a dying light bulb, it stretches. Born perhaps from the final evaporation of the last black hole, this particle of light begins its journey in a cosmos so vast and empty that it may travel for trillions of years without ever encountering another particle. Space itself has become a desert so immense that galaxies are now just ancient myths, their structures long dissolved into darkness. As the universe continues expanding, the photon's wavelength grows longer, its energy bleeding into the void until it's barely more than a whisper riding the curvature of spacetime. This is the era of the frozen horizon, a time when the temperature of the cosmos approaches absolute zero. There are no stars left to birth new photons, no atoms to absorb or re-emit them, just this single, lonely traveler, red-shifted into oblivion. Its journey is the universe's final act of radiation, a last flicker of information proving that something once existed here. When it finally fades, it won't be because it hits anything. There's nothing left to hit. Instead, its energy will dilute so completely that it ceases to be detectable, even in principle. The very concept of light loses meaning when there's no one left to see it. Imagine standing in that void, if such a thing were possible, and watching that photon's final moments. You wouldn't see anything because by this point your eyes, your brain, even the atoms that made you would have disintegrated eons ago. The photon's disappearance isn't an event, it's the absence of events. No fanfare, no collapse, just the quiet surrender of the last organized energy to the endless hunger of entropy. There's a tragic beauty in this ending. That photon could have been emitted by the first stars, their light now stretched beyond recognition. Or perhaps it was born in the fiery heart of a quasar, one of the universe's brightest objects, now reduced to this feeble glow. Its entire existence, from birth to fade, spans the entire lifespan of the cosmos, a thread connecting the beginning to the absolute end. And when it's gone, Nothing, not darkness, because darkness implies the possibility of light. Not cold, because cold is measured against heat. Just a perfect, unchanging equilibrium where time itself has no meaning. The universe doesn't end with a bang or a whimper, but with the last ripple fading from a pond that no longer remembers it was ever disturbed. Somewhere, right now, a piece of the universe is stretching faster than light can travel, and it will never stop. This isn't science fiction. It's eternal inflation, a theory suggesting our entire cosmos might just be one bubble in an endless, frothing sea of universes, each with its own rules of physics and its own destiny. Picture boiling water. Most bubbles pop quickly, but some merge or grow larger. Now imagine those bubbles are entire realities, and the boiling pot is a hyperdimensional spacetime factory, churning out new universes faster than minds can comprehend. At the heart of this idea is a twist on cosmic inflation, the explosive expansion thought to have shaped our early universe. In most models, inflation ends when its energy field decays, releasing heat and matter in a big bang. But what if some patches of space never stop inflating? Quantum fluctuations could create pockets where the field remains stuck in a high-energy state, continuing to stretch space exponentially while surrounding regions settle into stable universes like ours. The result, a self-replicating fractal where every inflating region spawns endless daughter universes, each isolated from the others by walls of forever expanding space. The implications are staggering. In this multiverse, physical constants become accidents of location. One bubble universe might have gravity 1,000,000 times stronger, making stars burn out in days. Another could have no weak nuclear force, preventing atoms from ever forming. Some might be so dense they collapse instantly into black holes, while others stretch so thin they can't even support particles. Our universe's delicate balance, the precise tuning that allows galaxies and life, isn't a miracle. It's just statistics. With infinite bubbles, a few are bound to be habitable by chance. What makes eternal inflation so compelling isn't just the diversity of possible worlds, but how it solves one of cosmology's deepest puzzles: why our universe appears fine-tuned for complexity. If inflation is truly eternal, there's no need for a designer or singular beginning, just an endless process churning out realities until, by sheer probability, one like ours emerges. It's the ultimate answer to the Goldilocks question: why is everything just right? Because in an infinity of wrongs, a few rights are inevitable. Yet for all its elegance, eternal inflation raises thorny questions. If new universes are constantly being born, what does time even mean on a multiversal scale? Can information cross between bubbles, or are they forever sealed off? And most unsettlingly, if our bubble is just one among countless others, does that make our eventual heat death or any ending meaningful in a grander sense? The theory isn't purely speculative. Some physicists hunt for evidence in the cosmic microwave background, searching for bruises where our bubble might have collided with another during inflation. Others model quantum tunneling between vacuum states, calculating the odds of new universes sprouting from old ones. The math suggests a startling possibility. If eternal inflation is real, the multiverse isn't just a place. It's a process, one without beginning or end, endlessly rewriting the rules of reality itself. So while we ponder our universe's fate, somewhere beyond the reach of our telescopes, another bubble is inflating right now. Its physics might be alien, its destiny unrecognizable, but in the grand tapestry of eternal inflation, every ending is also a beginning, one thread in an infinite, ever-growing fabric of existence. Imagine our universe not as a solitary bubble floating in nothingness, but as a sheet of paper drifting through a library of other sheets, each one a separate reality vibrating in higher dimensional space. This is brain cosmology, a radical framework where our entire cosmos exists on a membrane, or brain, floating in a higher dimensional bulk. According to string theory, these brains could be stacked close together like pages in a book, each hosting its own universe with its own laws of physics. And sometimes these pages collide. The implications are staggering. A collision between brains might not just be destructive, it could be creative. Picture two sheets of paper smacking together with enough force to ignite a new Big Bang, resetting the cosmic clock. Some theorists propose this is how our own universe began, the remnants of a cataclysmic brain collision 14 billion years ago. But it also suggests a cyclical model where universes collide, reboot, and repeat in an endless dance across higher dimensions. These collisions wouldn't look like anything we'd recognize. Higher dimensional physics suggests the impact would manifest as an all-pervasive energy flood, a uniform burst of heat and radiation rewiring the fabric of our universe from top to bottom. There'd be no warning, no localized epicenter, just an instant where the old laws of physics dissolve and new ones take their place. One moment, stars are burning as they always have. The next, the very concept of star might no longer apply. But here's where it gets truly mind-bending. If brains can collide once, they can collide repeatedly. Cyclic brain cosmology posits that universes might undergo endless cycles of expansion, collision, and rebirth, each time with slightly different parameters. Gravity could strengthen, dark energy might fade, or fundamental particles could gain new properties. Over infinite cycles, this could explain why our universe seems so finely tuned for complexity. It's just the latest iteration in a series of cosmic trials and errors. The wildest part, evidence for this might already exist. The cosmic microwave background, the afterglow of the Big Bang, contains faint temperature variations that some theorists argue could be bruises from a pre-Big Bang brain collision. Others suggest that gravitational waves, the ripples in spacetime from cataclysmic events, might carry imprints of higher dimensional physics if we develop sensitive enough detectors. Yet brain cosmology also raises existential questions. If our universe is just one membrane among many, does that mean all possible physics configurations exist somewhere in the bulk? Could there be brains where time flows backward, or where entropy decreases instead of increases? And if collisions are inevitable, does that make heat death irrelevant, just a pause before the next cosmic reset? This isn't just theoretical musing. Experiments at particle colliders like the Large Hadron Collider are searching for signatures of extra dimensions, tiny gravitons, leaking off our brain into the bulk. Even the holographic principle, the idea that our universe's information might be encoded on its boundary like a cosmic hard drive, finds a natural home in brain cosmology. Perhaps the most poetic idea is that brain collisions aren't endings at all, just transitions. A universe's destruction becomes another's creation, a cosmic passing of the torch through dimensions we can't see. It's a reminder that even the grandest scales of time and space might just be fragments of something larger, a multiverse where endings are beginnings and every collision writes a new chapter. The ground beneath your feet feels solid, unshakable, but what if it's an illusion? Some physicists argue that the very fabric of our universe might be perched on a precarious ledge, a state called a false vacuum. Think of it like a marble resting in a shallow dip on the side of a mountain. It seems stable, but given the right nudge, it could roll all the way down into a deeper valley, a true vacuum state where the laws of physics as we know them cease to exist. The terrifying part, this shift could happen anywhere at any time, rewriting reality at the speed of light without warning. Here's why this isn't just theoretical hand-wringing. In quantum field theory, the vacuum isn't empty space, it's a seething soup of potential energy. The laws that govern particles and forces emerge from how these fields balance across the universe. Right now, those fields are in what we call a local minimum, a stable-ish configuration that allows atoms, stars, and life to exist. But if a more stable, lower energy state exists, a global minimum, then our entire reality is fundamentally unstable. All it would take is a single quantum fluctuation in the right place to tip the scales, creating a bubble of true vacuum that expands faster than light, erasing the old physics in its wake. Picture it like this: if our universe were a glass of water supercooled below freezing, it would look liquid, but the slightest disturbance could flash freeze it instantly. Similarly, right now, the Higgs field, which gives particles their mass, seems to be in a precarious state. Calculations suggest its current energy level might not be the lowest possible. If it tunnels into a lower state, the ripple effect would be cosmic. Electrons could become too heavy to form atoms, quarks might stop bonding into protons, and the very concept of matter as we know it would vanish. The bubble's edge wouldn't just destroy things, it would redefine what destruction even means. The most unsettling part: we might never see it coming. A true vacuum bubble could originate billions of light years away, but since it expands at light speed, the first sign of its existence would be its arrival. There'd be no time to react, no chance to flee. One moment you're sipping coffee, the next the coffee and the cup and your hand no longer obey the same physics. The universe wouldn't end with fire or ice, but with a silent reconfiguration so total that concepts like universe or end might no longer apply. Not all physicists lose sleep over this, though. Some argue that if the false vacuum were so unstable, it likely would have decayed already in the 14 billion years since the Big Bang. Others counter that we might be in a surprisingly robust pocket of spacetime, shielded by sheer statistical luck. There's also the possibility that the true vacuum state doesn't exist at all, that our current laws are the most stable configuration. But until we can peer deeper into quantum field theory or detect echoes of other vacuum states in high-energy experiments, we're left with a haunting uncertainty. What makes this more than just a cosmic horror scenario is how it reframes our place in reality. We're not just passengers on a planet orbiting a star, we're actors in a universe that might be playing by temporary rules, a cosmic game of Jenga where the tower hasn't fallen yet. Every particle collision in accelerators, every distant supernova observed, is a tiny test of that stability. And if the day ever comes when the rules change, it won't be an apocalypse. It'll be a reboot, one where no one gets to hit save first. At the universe's end, time doesn't just slow down, it becomes a hall of mirrors where moments stretch into infinities. Picture a single observer, perhaps an advanced civilization huddled around the dying ember of the last black hole. From their perspective, each passing second might feel normal, but the universe outside their tiny pocket of existence is transforming into an unrecognizable stretch of frozen eternity. This isn't science fiction, it's the brutal consequence of relativity, where gravity and the expansion of space warp time itself into something unrecognizable. As the cosmos expands toward heat death, the few remaining structures, black holes, rogue planets, perhaps artificial habitats, will find themselves isolated in vast voids. The space between them stretches faster and faster, redshifting all light beyond visibility and cutting off communication forever. For observers near these final islands of matter, time dilation becomes extreme. A clock ticking on one of these remnants would run infinitely slower compared to the outside universe, where space stretches at an ever-accelerating pace. A single thought, a single heartbeat, might take trillions of years by external standards, yet to the observer, it feels like an instant. The closer the universe gets to maximum entropy, the more time itself becomes meaningless. With no new events, no energy gradients to drive change, there's nothing to mark the passage of time. It's like watching a frozen lake where no ice ever cracks, no wind ever stirs the surface. Even if consciousness could persist, the experience would be a single, unending moment, a present without past or future. The cruelest twist, the universe's final moments might never actually arrive from any local perspective. As black holes evaporate via Hawking radiation, their final milliseconds stretch into eons due to the intense gravity at their event horizons. An observer watching a black hole's last instant would see it fade asymptotically, always approaching zero, never quite reaching it. Time, in effect, becomes locked in an infinite slow-motion freeze frame where the end is perpetually almost here but never comes. For any remaining intelligence, this presents an existential paradox. If you're close enough to the last sources of energy to survive, time distorts so severely that the universe beyond your horizon effectively ends in a blink. But if you're outside, watching from a distance, those final structures seem to linger forever. The universe's death isn't a single event, it's a fractured, subjective experience where the very concept of now splinters into infinite variations. And then there's the haunting possibility that in the far, far future, new observers could arise from quantum fluctuations. Boltzmann Brain's self-aware configurations of particles that randomly assemble in the void might flicker into existence, each experiencing a phantom present disconnected from any coherent timeline. To them, the universe's death might feel like a fleeting dream or an endless loop of confusion, with no way to grasp the eons that came before. This is the ultimate irony of cosmic time. The universe began in a fiery singularity where time itself was born, and it might end in a way that renders time irrelevant, a flickering illusion stretched thin across an infinite canvas. For us now, seconds pass in familiar rhythm, but the deeper truth is far stranger. Time isn't universal. It's a fragile, local phenomenon, and at the universe's edge, it shatters completely. Black holes aren't just cosmic vacuum cleaners, they're existential shredders, tearing apart not just matter but the very information that defines it. At first glance, this seems like a grim dead end for the universe's story. If a black hole swallows a star, that star's composition, its history, even the potential life orbiting it, all seemingly vanish behind an event horizon erased from reality. But quantum mechanics throws a wrench into this bleak picture, insisting that information can never truly be destroyed. This paradox between gravity's appetite for oblivion and quantum physics' insistence on preservation has profound implications for how the universe itself might remember its own existence. Consider a book tossed into a fire. In classical physics, it burns to ash, its words lost forever. But at the quantum level, the information encoded in those pages isn't gone. It's scrambled into the heat radiation, theoretically recoverable if you could track every photon. Black holes present a far thornier challenge. Their intense gravity warps spacetime so severely that Hawking radiation, the faint energy they emit, appears random, carrying no trace of what fell in. For decades, physicists assumed the information was irretrievably lost, until breakthroughs suggested it might instead be imprinted holographically on the event horizon, like a cosmic hard drive storing data in Planck-scale pixels. Now scale this up to the universe's fate. If black holes eventually evaporate via Hawking radiation, does that mean the information they consumed is restored, or is it forever garbled? The answer could determine whether the cosmos preserves its history even in heat death. Some models suggest quantum entanglement might thread information through spacetime like invisible stitches, leaving faint echoes in the vacuum. Others propose that black holes aren't endpoints but transformers, repackaging information into new forms that could persist in the universe's quantum foam long after stars fade. The stakes are staggering. If information is preserved, then even in a dark, empty universe, the story of galaxies, civilizations, and every fleeting thought might still exist encoded in the fabric of reality itself. It's not resurrection, but a kind of cosmic archaeology where the universe's entire history remains etched into its bones. Conversely, if information is truly lost, then the cosmos isn't just dying, it's forgetting, one black hole at a time. This isn't just theoretical noodling. Experiments with quantum computers are testing how information behaves under extreme conditions, mimicking black hole dynamics in lab settings. And if we ever detect soft hair, a hypothetical zero-energy particles theorized to cling to black hole horizons, it could confirm that information isn't vanishing, just hiding in plain sight. The chilling possibility, information might persist but become so diffuse that reassembling it would require energies beyond imagination, like trying to reconstruct a symphony from the heat of a single match. In that case, the universe's epitaph wouldn't be written in stone or light, but scattered across an infinite void, a message no one could ever read. Imagine an intelligence witnessing the universe's final chapters not from the vibrant era of stars and galaxies, but from the silent, frozen depths of time's far edge. What would awareness even mean when the cosmos has cooled to near absolute zero, when black holes have evaporated into faint whispers of radiation, and the very concept of change has become a relic? This isn't just a thought experiment, it's a confrontation with the limits of meaning itself. If consciousness somehow persists in this era, it would exist in a reality so alien that our present vocabulary fails to describe it. No days or nights, no birth or decay, just a static expanse where the last flickers of thought unfold against an unchanging backdrop. One possibility is that any surviving minds would have long shed their biological origins, existing as self-sustaining patterns encoded in degenerate matter or quantum fields. They might dwell near the last energy sources, perhaps harnessing the Hawking radiation of evaporating black holes, stretching each joule of power across millennia of subjective experience. To conserve resources, their thoughts could slow to glacial speeds, with centuries passing between each synaptic equivalent. Their perception of time would warp grotesquely. A single moment of reflection might span what we'd consider an entire geological epoch. Communication between these far-flung intellects would be impossible. Space's expansion would have severed all connections, leaving each alone with its memories in an oceanic silence. Yet even this bleak scenario raises deeper questions. Could an intelligence truly remain conscious without novelty? Our brains thrive on input sensory data, social interaction, the relentless churn of a dynamic world. Strip that away, and does awareness collapse into a feedback loop of recycled memories? Some philosophers argue that consciousness isn't just computation. It's intrinsically tied to interaction with an external reality. In a universe where nothing new occurs, the very act of thinking might become indistinguishable from hallucination. The last mind could spend eternity reliving the same fragments of a long-dead civilization, unsure whether its recollections are history or phantom limbs of a frozen psyche. But there's a stranger alternative. If the universe's expansion never stops, quantum fluctuations, however rare, might still spawn fleeting pockets of complexity. Boltzmann brains, those self-aware configurations arising from sheer randomness, could flicker in and out of existence. These phantoms would wake fully formed, armed with false memories of lives never lived, only to dissolve moments later into the void. Their experiences, however brief, would be the universe's final whispers of subjectivity, a hall of mirrors where reality and illusion blur. To such ephemeral entities, the cosmos wouldn't appear old or dying. It would simply be the empty stage upon which their momentary drama plays out. Perhaps the most unsettling prospect isn't extinction, but transformation. Advanced civilizations might engineer their own successors, self-replicating machines that encode not just data, but the essence of experience itself. These descendants could rewrite their own perception of time, treating the heat-death as a navigable landscape rather than a terminus. A single second could be subjectively stretched into an eternity through computational slowing, creating the illusion of an unending present. Or they might fragment their consciousness into parallel threads, simulating the vibrancy of a lost universe within sealed pocket dimensions. In this view, the end isn't oblivion, it's metamorphosis, where the line between mind and cosmos dissolves. Ultimately, the fate of consciousness may hinge on something deeper than physics, the nature of meaning itself. We instinctively tie purpose to growth, discovery, and legacy, concepts that wither in a post-entropic universe. But what if meaning isn't bound to narrative or progress? The last intelligence might find solace in pure being, a Zen-like acceptance of the eternal now. Or it could rage against the dying of the light, etching its defiance into the fabric of space-time before the final darkness. The universe won't decide what matters, the last mind will. And in that solitude at the edge of time, the answer might be simpler than we think. To witness is to resist, to remember is to endure. What if the speed of light isn't constant not just through different media, but across cosmic time itself? This radical idea, known as variable speed of light cosmology, turns our understanding of the universe's fate upside down. Proponents suggest that in the early universe, light might have traveled millions of times faster, explaining how distant regions appear homogenized despite having no time to communicate. But here's the mind-bending implication. If light's speed can change once, it might change again. Future civilizations could witness physics rewriting itself in real time, with the fabric of causality stretching and warping in ways we can barely imagine. Then there's emergent gravity, a concept that treats gravity not as a fundamental force, but as a side effect of entropy playing out across the holographic surface of spacetime. Think of it like the way temperature emerges from countless molecular collisions, a collective behavior with no single source. In this view, as the universe expands and entropy increases, gravity's very nature could transform. Distant galaxies might not be accelerating away from us due to dark energy. They could be responding to a fundamental shift in how gravity operates on cosmic scales. It's as if the rules of the game are changing midway, with the universe's expansion acting less like an explosion and more like a phase transition in some vast, unseen medium. Some theories go even further. Quantum gravity suggests spacetime itself might freeze like water turning to ice as the universe cools. What we perceive as the smooth continuum of three dimensions could fracture into discrete, grainy units, a cosmic shattering that would render motion itself impossible. Others propose that dark matter isn't particles, but shadows cast by parallel universes brushing against ours in higher dimensions, their gravitational influence waxing and waning as membranes move in the bulk. The stakes, our predictions about the universe's end, might be like forecasting an avalanche while misunderstanding the properties of snow. If light speed decays over eons, distant galaxies could wink out not from expansion, but because their light never reaches us. Proton decay might accelerate if quantum tunneling rates aren't fixed. Even black hole evaporation could follow different rules if Hawking radiation turns out to be an approximation of deeper physics. These aren't just tweaks to existing models, they're complete reimaginings of cosmic destiny. Perhaps the most intriguing possibility comes from cosmological natural selection, where universes evolve through black hole births like biological reproduction. In this scenario, our universe's constants are fine-tuned not by accident, but because previous iterations selected for black hole-rich physics, the implications for the far future. Our cosmos might be preparing its own successors right now, with each singularity potentially birthing a new universe with slightly mutated laws. The cycle wouldn't be eternal, just long enough for physics to explore every survivable configuration. What ties these ideas together is their challenge to permanence. We assume the rules we observe today held true in the past and will persist forever. But history shows physics is full of phase transitions, moments when underlying rules shifted abruptly. The electromagnetic and weak forces unified until the early universe cooled enough to split them. Quarks froze into protons shortly after. Who's to say there aren't more transitions ahead? The universe's finale might not be a predictable fade to black, but an unscripted metamorphosis, one last, magnificent changing of the cosmic guard. For now, these theories remain speculative, their mathematics sprawling across whiteboards in institutions worldwide. Yet they share a thrilling common thread. The universe might have more surprises up its sleeve than our current models dare suggest. The same creativity that birthed relativity and quantum mechanics could be seeing its next revolution in theories that don't just predict the end, but redefine what end even means. What if the universe isn't the ultimate reality, but a simulation running on some unfathomable computer? Suddenly, the question of how everything ends takes a sharp turn because the rules aren't written by physics alone, but by the intentions of whoever or whatever launched the program. Would the architects shut it down once their experiment concludes? Could they hit reset and run it again with tweaked parameters? Or might they simply let it fade into neglect like an old server left humming in a forgotten data center? Consider the shutdown scenario first. If our universe is a simulation, its end might not be a natural process at all, but a deliberate termination. Picture a lab where researchers simulate early universe conditions to test theories. Once they have their data, they power off the system. Applied to us, this could mean an abrupt cutoff with no warning. One moment, reality unfolds as usual, the next, absolute nullity. No heat death, no big crunch, just an instant where all conscious experience winks out. The unsettling part, we'd never know. There'd be no artifacts, no cosmic clues, just silence. But what if the simulators choose to reboot instead? Cyclical universes take on new meaning if each iteration is a fresh run of the same base code. Cosmic parameters, gravity's strength, dark energy's pull might be adjustable settings rather than immutable laws. A reboot could explain the eerie fine-tuning of our universe. Maybe we're version 1001, each trial refining the simulation toward some unknown goal. Evidence might lurk in mathematical anomalies repeating patterns in cosmic constants, or glitches in quantum behavior that hint at underlying programming limits. Then there's the most haunting possibility, indifference. The simulation keeps running, but its creators lose interest, leaving it to churn toward heat death unsupervised. Civilizations rise and fall, black holes evaporate, and eventually entropy maxes out, all while the servers continue draining power in some higher dimensional basement. In this scenario, the universe's fate mirrors our own digital graveyards, abandoned virtual worlds filled with frozen avatars, their stories unfinished. Simulation theory also reshapes how we think about information preservation. In a programmed reality, data might not be lost when stars die, it could be logged externally. The entire history of the cosmos, down to your last thought, might exist in a master archive we'll never access. This twists the Boltzmann Brain paradox. If consciousness can emerge from random fluctuations inside the simulation, could it also be a debug tool, a way for the simulators to check their work? Of course, testing these ideas borders on the impossible. Any evidence we find could itself be part of the simulation's design, but the philosophical implications are staggering. If we're code, then free will might be an illusion, entropy just a variable, and the universe's end someone else's decision. Or worse, a system crash no one's left to fix. Yet there's a strange comfort here too. If the universe is a simulation, its ending isn't oblivion, it's a transition. The data that makes up reality might be repurposed, recompiled, or even studied. Our struggles, our art, our love for the night sky could all be preserved, not in atoms but in bits. The final screen might read, "Game over," but the game itself could live on, somewhere beyond the edges of the only reality we've ever known. Quantum gravity is the universe's greatest unsolved puzzle, a glaring crack in our understanding of reality that could reshape everything we know about how the cosmos ends. Right now, we have two sets of rules: quantum mechanics, which governs the microscopic world of particles, and general relativity, which describes the gravity shaping galaxies and black holes. Both work flawlessly in their own domains, but when they collide, like at the center of a black hole or the first moments of the Big Bang, the math breaks down into nonsense. This isn't just an academic headache. It means our predictions about the universe's ultimate fate could be completely wrong, built on a foundation that's missing its most critical piece. Take black hole evaporation. Stephen Hawking showed that black holes slowly leak radiation and vanish, but quantum mechanics insists the information they swallow can't be destroyed. So where does it go? Without a theory of quantum gravity, we're left with paradoxes that sound like cosmic magic tricks, information disappearing into a singularity only to reappear as random thermal noise. If we're misreading black holes' final act, we might also be wrong about how they shape the universe's long-term evolution, those last evaporating black holes in the distant future. Their deaths could leave behind more than just empty space, maybe new particles, hidden dimensions, or even baby universes we can't yet imagine. Then there's dark energy, the mysterious force accelerating the universe's expansion. Is it truly constant, as Einstein's cosmological constant suggests, or could it fluctuate due to quantum gravity effects we don't yet understand? Some theories, like loop quantum gravity, propose that spacetime itself is granular at the tiniest scales, a foamy sea of Planck-length bubbles. If true, dark energy might not be smooth and uniform but churn with quantum turbulence, potentially weakening or surging over cosmic timescales. That could turn our current projections upside down, replacing the slow fade of heat death with a bumpy ride toward an entirely different finale. Even the Big Bang's afterglow hints at gaps in our knowledge. The cosmic microwave background's temperature fluctuations align eerily well with models of cosmic inflation. But inflation relies on a quantum field we've never directly observed. Could quantum gravity reveal that inflation was just the first act in a larger drama? String theory, for all its controversy, suggests universes might collide in higher dimensions, igniting new bangs in an endless cycle. Without a quantum theory of gravity, though, these ideas remain speculative daydreams. The stakes couldn't be higher. If quantum gravity introduces new forces or particles at extreme energies, they might alter proton decay rates, tweak black hole evaporation speeds, or even open escape hatches from heat death. Imagine a civilization in the far future discovering that spacetime itself can be rewoven, like a frayed tapestry repaired from within. Or learning that the universe's expansion isn't inevitable, just a temporary phase before quantum gravity's hidden rules kick in. Right now, experiments like the Large Hadron Collider and gravitational wave detectors are hunting for clues. A single anomaly in particle collisions or an unexpected ripple in spacetime could upend everything. Until then, our cosmic expiry date remains a question mark written in two conflicting languages, waiting for a Rosetta Stone to reveal the final word. The universe operates like a cosmic clock, winding down every tick dictated by the unrelenting laws of thermodynamics. These aren't just rules for steam engines or refrigerators. They're the invisible scaffolding shaping everything from the birth of stars to the silence of heat death. The first law, conservation of energy, tells us the universe's total energy remains constant, never created or destroyed, only transformed. But here's the catch: while energy stays fixed, its usefulness decays. Imagine a campfire burning down to embers. The heat hasn't vanished, it's just dispersed into the night air where no one can warm their hands by it anymore. That's the second law in action. Entropy, the measure of disorder, always increases. Now scale that up to cosmic proportions. Every galaxy, every star, every living cell exists because of energy gradients, regions where heat and order concentrate temporarily. Suns burn by converting hydrogen into helium, creating pockets of low entropy that fuel life and complexity. But like a battery draining, these gradients flatten over time. The universe started with a colossal energy dump, the Big Bang, and has been slowly spending that inheritance ever since. Even black holes, those cosmic vacuum cleaners, contribute to entropy's rise. When matter falls past an event horizon, it scrambles information so thoroughly that entropy skyrockets. A single stellar mass black hole carries more entropy than all the stars in its host galaxy combined. This relentless march toward disorder isn't just a slow fade, it's a funnel narrowing all possible futures. The third law of thermodynamics adds the chilling footnote. As temperature approaches absolute zero, entropy approaches a minimum value, but only for perfect crystals in ideal conditions. The universe is anything but ideal. In the far future, when particles are spread thinner than ghosts and no stars remain to create new heat, entropy will effectively max out. No more work can be extracted, no more structure can form. The cosmos becomes a lukewarm bath where every molecule is equally likely to be anywhere, a state physicists call thermal equilibrium. But here's where thermodynamics gets hauntingly creative. These laws don't prescribe a single ending. They define boundaries within which all possible endings unfold. Heat death is just the default, like a ball rolling to rest at the bottom of a valley. Other scenarios, the Big Rip, vacuum decay, are exceptions where external factors like dark energy's wild card tilt the playing field. Even time's arrow, that one-way flow from past to future, emerges from entropy's rise. Without increasing disorder, there'd be no way to distinguish yesterday from tomorrow. The irony, thermodynamics birthed the very complexity it will ultimately erase. Life, stars, even thoughts are temporary eddies in entropy's stream, local decreases in disorder paid for by larger increases elsewhere. Your body right now is a pocket of improbability, a statistical fluke sustained by the sun's fury and Earth's intricate cycles. In the long run, the universe collects its debt. Yet within these ironclad rules, glimmers of defiance flicker. Some theorists speculate about Maxwell's demon, a hypothetical being that could sort particles to reduce entropy. Others point to quantum fluctuations that might, given infinite time, spontaneously reboot order. But thermodynamics laughs at quick fixes. Any local order created would require even greater disorder elsewhere, like shoveling snow into piles only to realize you've made the rest of the driveway icier. So when we peer into the cosmic abyss, we're not just seeing darkness, we're reading a ledger. Every galaxy's glow, every black hole's whisper is an entry in thermodynamics' grand accounting. The numbers never lie, the balance always comes due, and the final entry, written in particles too cold to stir and space too vast to matter, will simply read equilibrium. The cosmic microwave background is more than just a relic of the Big Bang. It's a time capsule encoding the universe's fate in faint ripples of heat, stretching across the entire sky. This afterglow from when the cosmos was just 380,000 years old carries patterns so subtle they require satellites like Planck to map their whispers. Yet within those minute temperature fluctuations, variations of just 1 part in 100,000, lies a treasure trove of clues about how everything ends. Take dark energy's fingerprints, for instance. The way galaxies cluster today traces back to those primordial density variations imprinted on the CMB. By comparing these ancient wrinkles with modern cosmic structures, astronomers can measure how dark energy has altered the universe's expansion rate over billions of years. Some models suggest the CMB's large-scale patterns hint at dark energy growing stronger over time, a potential smoking gun for a future Big Rip. Others find anomalies in how the afterglow's light becomes polarized around galaxy clusters, possibly signaling new physics that could upend our predictions. Then there's curvature. The CMB acts like a cosmic yardstick. The apparent size of its temperature patches reveals whether space is flat, closed like a balloon, or open like a saddle. Current data overwhelmingly favors flatness, meaning the universe will likely expand forever rather than recollapse. But there's a catch: measurements at even finer precision might uncover slight curvature masked by statistical noise. A closed universe, no matter how slight, could still doom us to a big crunch in the far future. Perhaps most tantalizing are the B-mode polarization patterns, swirling imprints in the CMB that could stem from gravitational waves rippling through the infant universe. Detecting these could confirm cosmic inflation's violent origins while revealing energy scales that dictate vacuum stability. If certain B-modes are found, they might indicate our universe is perched on a false vacuum cliff, vulnerable to sudden decay. Future observatories like the Lightbird satellite aim to hunt for these whispers with unprecedented sensitivity, potentially rewriting our expiration date. The CMB's greatest gift is its duality. It's both a snapshot of the past and a prophecy of the future. Its photons have traveled for over 13 billion years, witnessing the universe's entire history while carrying encrypted messages about its finale. As technology advances, we might decode even subtler signals, perhaps evidence of other universes bumping against ours in a multiverse foam, or relics from a pre-Big Bang cycle encoded in anomalies at the largest scales. What makes this pursuit so profound is its humbling uncertainty. The same CMB data that cemented our understanding of cosmic evolution now teases us with questions it can't yet answer. Like a crossword puzzle missing half its clues, the Afterglow's full story remains tantalizingly out of reach for now. But with every new generation of telescopes, we peel back another layer, inching closer to reading the universe's final chapter in its first light. Gamma-ray bursts are the universe's flashbangs, sudden, catastrophic explosions of energy so intense they outshine entire galaxies for a few fleeting seconds. These cosmic firestorms, often born from collapsing hypergiant stars or colliding neutron stars, don't just light up the cosmos, they scorch it. Imagine a beam of energy so focused it could sterilize planets thousands of light years away, packing more power in milliseconds than our sun will emit in its entire 10 billion-year lifetime. While we're safe from these celestial death rays today, they serve as brutal previews of the chaos that could unfold as the universe ages and stellar evolution grows more extreme. In the far future, as galaxies exhaust their gas supplies and star formation dwindles, the remaining stars will be mostly massive, unstable beasts prone to violent ends. Hypernova supernovas on steroids could become commonplace, each one unleashing gamma-ray bursts like cosmic artillery. These explosions wouldn't just destroy nearby systems, they'd rewrite the rules of habitability across entire galactic neighborhoods. Picture a galaxy where life's survival isn't about finding the right planet, it's about dodging lethal barrages of radiation from dying stars too colossal to fade quietly. But here's the twist: gamma-ray bursts might also accelerate the universe's decay. Some models suggest these outbursts could trigger vacuum metastability events, quantum domino effects where the high-energy collision nudges space-time into a lower energy state. It's like a spark landing on a powder keg of false vacuum. One burst in the wrong place at the wrong time could theoretically spawn a bubble of new physics that expands at light speed, erasing the old universe in its wake. The odds are vanishingly small, but in an eternity, even the rarest events become inevitable. The broader lesson is clear: the universe doesn't just fade, it fights. Long before the last stars gutter out, regions of space could endure apocalyptic spasms of radiation, gravitational waves, and particle showers. These aren't just fireworks, they're symptoms of a cosmos growing increasingly hostile as its energy gradients flatten. For civilizations clinging to existence in this era, survival might mean burrowing into the hearts of dead stars or crafting shields against radiation storms we can barely comprehend today. Yet amid this violence, there's a strange irony. Gamma-ray bursts, for all their destructive fury, are also cosmic lighthouses, beacons that illuminate the universe's structure and history. Their afterglows reveal the composition of distant galaxies, the interstellar medium's density, even the geometry of spacetime itself. In the end, they're both destroyers and teachers, carving their lessons into the fabric of everything. Science paints the universe's end in stark equations: heat death, vacuum decay, the slow unraveling of matter itself. But humanity has grappled with eternity long before telescopes and particle accelerators, weaving narratives that span from resurrection to rebirth, from divine judgment to endless cycles. These philosophical and spiritual visions don't just contradict scientific predictions, they reveal how deeply our fear of nothingness shapes the stories we tell about existence. Take the ancient Norse concept of Ragnarök, a fiery apocalypse where gods and monsters clash in a final battle. The earth sinks into the sea, and a new world rises from the waters, green and fresh. It's a far cry from heat, death, silent fade, yet both share a curious thread, the idea that destruction isn't absolute. For the Vikings, the end was a prelude to renewal. Modern physics flirt with similar notions in cyclical cosmology, where big bangs might follow big crunches in an endless loop. The difference, one is myth, the other math, but both betray a refusal to accept that anything, even the cosmos, ends for good. Eastern traditions offer another lens. Hinduism and Buddhism envision time not as a linear march toward oblivion, but as a wheel turning through ages of creation, preservation, and dissolution. In these cosmologies, the universe breathes, expanding and contracting not just in space, but in meaning. The Hindu Kalpa, a day of Brahma, lasts 4.3 billion years only to repeat anew. Here, entropy isn't a slow descent into disorder. It's the natural exhale of a system preparing for its next inhale. Compare this to the Boltzmann Brain paradox, where quantum fluctuations might spawn temporary consciousness in the void. Both frameworks suggest that even in eternity, moments of awareness flicker like fireflies in the dark, ephemeral but recurring. Abrahamic faiths, by contrast, often frame the end as a divine finale, a moment of reckoning where time itself is unrolled like a scroll. Christianity's Book of Revelation describes stars falling like figs, a new Jerusalem descending from heaven, and a final battle between good and evil. Islam's Quran speaks of mountains scattering like wool, the sun coiled like parchment. These visions replace scientific detachment with moral urgency. The universe doesn't just end, it culminates. For believers, this transforms nothingness from a void into a threshold. The moment before an eternal, transcendent reality begins. Philosophers, untethered from dogma, dissect nothingness itself. Heidegger pondered being toward death, arguing that confronting finitude gives life meaning. Sartre saw existence as a fragile spark against the cold silence of infinite spaces. But it's Buddhism's sunyata, or emptiness, that offers the sharpest contrast to Western dread. Here, nothingness isn't absence, it's the fundamental nature of reality, a web of interdependence where all phenomena arise and pass away. In this view, fearing the universe's end is like fearing the dissolution of a rainbow, beautiful but never solid to begin with. What unites these threads is the human insistence that endings must mean something. Science offers cold comfort. The universe doesn't care if we find purpose in its demise. Yet our ancestors painted the void with gods and rebirths, and our physicists theorize multiverses and quantum resurrections. Perhaps the deepest truth lies in this tension that whether through prayer or particle physics, we're compelled to whisper stories into the dark, hoping something somewhere might whisper back. Humanity's entire written history, every war, every invention, every whispered word of love spans less than a heartbeat against the universe's timeline. We emerged so late in cosmic history that the first stars had already lived and died, recycling their ashes into the planets beneath our feet. Our species has existed for roughly 300,000 years, a blink so brief it wouldn't even register on a calendar stretching back to the Big Bang. Yet here we are, staring into the abyss of deep time, desperately trying to carve our names into eternity. Consider time capsules, those humble metal boxes buried with photographs and letters, sealed with the hope that some future hand might rediscover them. The Voyager golden records, hurtling through interstellar space with greetings from Earth, push this ambition even further. These artifacts are more than nostalgia, they're defiance. A refusal to accept that our stories will vanish without a trace. But the brutal truth is that even our sturdiest monuments are ephemeral. Pyramids erode. Satellites spiral into stars. Digital data degrades within decades unless actively preserved. Against the trillion-year march toward heat death, these attempts feel like writing in sand at low tide. Yet there's a sublime audacity in these efforts. Projects like the Lunar Library, which etched 30 million pages of human knowledge into nickel discs and landed them on the moon, or the Svalbard Global Seed Vault, safeguarding our biodiversity in Arctic ice, aren't just practical, they're philosophical. They force us to ask, what's worth preserving when time itself is the enemy? The answer varies wildly. Some would save DNA sequences, the blueprint of life. Others would encode mathematics, the universe's native language. A few might prioritize art, the ineffable spark of human creativity that no algorithm can replicate. The real challenge isn't just survival, but legibility. Imagine a being or a machine unearthing one of our archives a billion years hence. Would they grasp that a photo of a sunset was more than a wavelength log? Could they decode the emotional weight behind a child's drawing or the anguish in a war poem? This is the problem with Rosetta Stones. They assume the future shares our context. But as languages evolve and cultures transform, meaning dissolves. The very atoms in our storage mediums might decay, leaving behind garbled noise. Perhaps the most poignant realization isn't that we'll be forgotten, it's that the universe never needed remembering in the first place. The cosmos thrived for billions of years without witnesses, and it will persist for billions more after we're gone. Our drive to leave marks says less about the universe's indifference than about our own hunger for significance. We're ephemeral patterns in the void, insisting against all odds that our brief flicker mattered. The paradox, in confronting our impermanence, we've created something timeless, the act of questioning itself. Every telescope pointed at the stars, every equation scribbled in pursuit of dark matter, every aching line of poetry about mortality, these aren't just preparations for an end. They're proof that even in the face of oblivion, curiosity and wonder persist, and that, more than any artifact, might be our real legacy, not the data we leave behind, but the fact that we looked up at all. So where does this leave us? After all the theories, the equations, the glimpses into possible cosmic endings, the truth remains humbling. We don't yet know how the universe will conclude. The most plausible scenarios, heat death, the big rip, vacuum decay, paint vastly different final acts, yet they all share one haunting certainty. Time, as we understand it, will run out. Whether it's the slow fade of particles drifting into darkness or the violent unraveling of spacetime itself, every path leads to a reality where the word future no longer holds meaning. But here's the paradox buried in these predictions. The same physics that foretell the universe's end also made our existence possible, those distant dying stars. Their explosions forged the carbon in your bones, the dark energy accelerating cosmic expansion. It's the reason galaxies could form at all. We're not just bystanders to this story, we're products of its unfolding, temporary flickers of awareness in a cosmos that will one day forget itself. That's the real revelation. The universe's impermanence isn't just a scientific fact, it's a mirror. If all this grandeur, from swirling nebulae to beating hearts, is destined to dissolve, then our moment under the stars becomes staggeringly rare. Think of Earth's history compressed into a single day. Human civilization arises in the last thousandth of a second before midnight. Our entire collective memory, every poem, every invention, every act of love exists in that blink. Yet here we are, tracing equations that predict the death of light itself. Perhaps the most profound mystery isn't how the universe ends, but why it allowed itself to be known at all. For billions of years, there were no eyes to see the galaxies, no minds to ponder entropy. Now, briefly, there are. That collision of chance and inevitability, a universe capable of understanding its own fate, may be the closest thing to magic science has ever uncovered. So let's end with a question that lingers long after the theories fade. If the universe is finite, does that make every moment within it infinitely precious? Not because some divine hand decreed it so, but because against the backdrop of cosmic time, existence, your existence is a vanishingly improbable spark in the dark. The universe may not remember us, but right now we remember it, and that changes everything.